We're going to do Chapter 7 today. But before we do Chapter 7, on Wednesday we're doing a really neat lab determining the empirical formula of magnesium oxide, lab number 8. It's an interesting lab and it's a little bit scary. So I wanted to go over it before we did it. Empirical formulas, we covered those back in Chapter 4. We said the empirical formula, lowest whole number ratio of the elements in the compound. So basically it's the mole ratio. CH2O means a mole ratio of 1 carbon, 2 hydrogens, 1 oxygen. An example is the sugar glucose. C6H12O6. Now that's the molecular formula. In order to get to the actual empirical formula, what you have to do is look at the subscripts here. You want to pick out the smallest and divide everything by the smallest. 6 is the smallest, so this goes to 1, 2, and 1. Empirical formula, CH2O. The empirical formula is what you get from analysis, and that's what we're going to do. But it really doesn't tell you too much more about the molecule except for the mole ratio of the elements. For example, we said glucose and acetic acid have the same empirical formula, but obviously they're very different compounds. Now, what we're going to do in this lab is we're going to burn magnesium metal. This will form magnesium oxide, and we're going to determine the empirical formula of magnesium oxide. Now, we all know enough chemistry by now that we know the answer. Okay, not a surprise, we all know the answer. But it's just kind of a neat exercise. It's an oxidation reaction. The metal's reacting with oxygen in the air. Magnesium burns with an incredible bright white light. It's very dangerous. It's extremely hot. As a strip of the metal burns, that's what we have here, it's converted from the metal to this little tingly white powder. It kind of falls apart as it goes. In order to keep this from falling apart, we're going to actually do our burning using this strip of magnesium in a crucible. So this is what our magnesium ribbon looks like. What you'll do is take this, it's about a foot long or so, and you'll wrap it gently around a pencil or a pen so that it fits inside of the little crucible. Now you want to make sure of a couple things. Make sure that the metal itself is touching the bottom and or the sides, and that it's not compacted so much that air can't get to it. We're going to take this guy, put it on a ring stand with a clay triangle, something like this, put a Bunsen burner under it, and we are going to literally heat the heck out of it. Heating the heck out of it, yes. When it gets nice and hot, the magnesium itself will catch on fire. This is extremely hot and somewhat dangerous. You really need to wear your goggles. You really need to remember everything is really, really hot. When the magnesium is finished burning, again, you will note everything is literally red hot. Don't touch anything, right? Keep your goggles on. We're left with this little bit of powder in the bottom. All right, this powder that's in the bottom actually weighs more than the magnesium we started with, because the magnesium is still there, but we've added oxygen. So what we're going to do, determine the empirical formula, we need to know moles of magnesium and moles of oxygen, so we get our mole ratio. We're going to weigh the empty crucible. We're going to add the magnesium, subtract the two weights, and get the mass of magnesium. Once we have the mass, we can convert this to moles simply by dividing by the molar mass. Mass over molar mass is moles. Now that's going to give you a number. I have no idea what your number is. There is no right answer. I'm going to make one up, just so we have a number to work with. I'm going to call it 0.015. Just made it up. All right, now we have this crucible with the gunk in it. We are going to weigh the crucible plus the gunk, that's the product. Subtract that from crucible plus magnesium to get the mass of the oxygen that we've added. Once we know the mass, again, mass over molar mass gives us moles of oxygen. Call that Y. And again, I made up a number. Now, the empirical formula is this mole ratio. We have a number for magnesium, a number for oxygen. Right now, our empirical formula looks like this. Magnesium X, oxygen Y. The numbers I made up are that. Well, we want integers, number one. We don't want these fractional coefficients. So what we do is we will take the smallest of the two, whichever it happens to be, and divide it, everything by it. So 0.015 is the smallest here. That divided by itself is 1. 0.016 divided by 1.5 is 107. So our second take on our empirical formula is this. Finally, it has to be an integer. So we're going to look at our 107 and say to make that an integer, we're going to make it a 1. And say our empirical formula is MgO. Any questions? Once again, everything is red hot. Really hot. You have to be really careful. Please remember that. Read the procedure. Make sure you know what to do. The procedure actually talks about putting a lid on the crucible. Ignore all the lid stuff. No lids. Any questions? Well then, let's move on to Chapter 7. Chapter 7, Aqueous Solutions. Going to be lots of pretty pictures in the first half of this. Going to talk first about dipoles in molecular compounds, the concept of electronegativity and polar covalent bonds. Then we're going to look at how the polar nature of water allows the dissolution of ionic compounds. We'll talk about the concept of solubility, some definitions. Expanding on that, we will do electrolytes and non-electrolytes. These solutions conduct electricity, these do not. Finally, we will get to molarity. This is the first thing we will do, this mathematical. Have a bunch of problems on molarity. Basically, it's the number of moles of a compound in solution divided by the number of liters. And finally, we will look at dilutions. If you take a solution of known concentration and add water, how do you figure out the new concentration? Any questions before we get started? then, we've talked about bonding a lot. Okay, we said there were two basic types. There is covalent bonding, where we share electrons, and there is the other limit, which is ionic bonding, where we totally transfer an electron. In reality, most compounds, the bonding is somewhere between these two limits. Let's look at what we said about simple covalent bonding. If we're going to make Cl2, here we have chlorine. Chlorine group 7 valence electrons. We would bring another chlorine up to it so that we could share these two electrons between the two atoms. This is our covalent bond. When we rewrite this using the dash nomenclature, it looks kind of like this. Now, in a case like this, the sharing of these electrons between the two atoms is going to be essentially perfect. That's because they're the same atom. Most compounds, the two atoms connected in a covalent bond are not identical. And we'll see that that means that this sharing is typically far from perfect. Let's consider two molecules. This represents hydrogen gas, H2, and this represents hydrogen fluoride, HF. They're both molecular compounds. They both have a single covalent bond between them. We are going to use what's known as an electrostatic potential map to explore the electron distribution in these covalent bonds. Now, electrostatic potential map, this is something you do on a computer. You start out by taking your molecule. You ask your computer to calculate what's known as a molecular orbital. The molecular orbital will tell you where the electrons are around a molecule. Let's do this first with hydrogen. First of all, we tell it to take our two hydrogen atoms bonded covalently and calculate where the electrons are. It will do something like this, and we'll wind up with a surface. This surface basically is an estimate of where you could expect to find the electrons 90% of the time. So 90% probability within this surface you will have the electrons. Next thing you do is you tell your computer to run over the surface here, back and forth, up and down, and calculate how many electrons there are. That is the electron density all over the surface. Once you have that, you use a color code. If there is electron deficiency, you color it blue. If there are excess electrons anywhere, you color it red. And there's a spectrum in between. So, for hydrogen, we do our coloration, and we wind up with something that looks like lime. Okay, this tells us that the electron distribution is pretty much uniform over the entire molecular orbital. Now that was expected because our two hydrogens are identical atoms. When we go over to HF, we see something different. We're going to do the same exercise. We start by asking what the molecular orbital looks like. and we get a slightly different looking surface. It's kind of lopsided relative to the elements, and it's got an odd shape to it. Next, we ask it the electron density all over the surface. And what we see is something very different. Down here by the hydrogen, we have electron deficiency. That's shown by the blue. That means a positive color down here. And here by the fluorine, we have excess electrons, negative charge, and again, it's all lopsided. What's happening here is that the fluorine is attracting the electrons towards itself and away from the hydrogen. This makes this bond very, very polarized. When we have a polar covalent bond like this, we can show it using a dipole moment. And basically that's an arrow with a cross on one end. This is the positive end of our bond. This is our negative. So what we have here is a polar covalent bond where the fluorine has attracted the electrons, pulled them towards itself, leaving the poor hydrogen here very positive. Now, why does this happen? It's the concept of electronegativity. Electronegativity is a number. It goes from 0 to 4. Fluorine is the most electronegative element. These guys down here are the most electropositive. Typically, electronegativity will decrease as you go down a group and will decrease across as you go through a period. Now, with HF, we're dealing with hydrogen and fluorine, 2.2 and 4. Fluorine, electronegativity measures the ability of an atom to attract the electrons towards itself. So fluorine is sucking all the electrons in that covalent bond towards itself. That's why we get the polar covalent bond. Now, polar covalent bonds will become even more important to us when we hit chapter 8. But this chapter is about solubility, things in water, molarity. So here we're going to be dealing with water, hydrogen and oxygen. Well, oxygen is right here next to fluorine. It's also very electronegative. Our prediction would be that the hydrogen-oxygen bond in water will be polar, just like HF was. Any questions? Well, let's move on to water then. Let's start off by constructing the Lewis structure. Oxygen is in group 6. It will have 6 valence electrons. Hydrogen, group 1, 1 valence electron. We need 2 electrons per bond, so let's just stick them in like this. We'll convert these into dash bonds, and that's our Lewis for water. Now, I have drawn this with the 2 hydrogens here on the same side of the oxygen, right here. The reason I did that isn't entirely arbitrary. I could have done it the other way. The reason I did it this way is because this approximates what the geometry of water really is. We will have two hydrogens on one side, a lone pair of electrons, and another lone pair of electrons. So, water actually in 3D looks like this. We refer to this geometry as being bent. Okay, bent. Go up and down. It's bent. Why is it bent? It's bent because there are four things around our central atom that have electrons. Two unshared pairs and two covalent bonds. There's a theory called valence shell electron pair repulsion. And what this basically tells you is that whenever you have things with electrons around the central atom, the geometry will rearrange itself such that the electrons are as far apart as possible. And that defines the geometry of the molecule. This is a little video that kind of shows it. If we had a central atom right here, and we had two either bonds or something, these are electron pairs, the geometry, the way that these could get the furthest apart, would be as if they were in a straight line, that is, linear. If we brought in a third one, we would wind up with a triangle. And bringing in the fourth, like we have in water, we get geometry that's known as tetrahedral. Tetrahedral, all of the bond angles are 109. Our central atom is here sitting up off the bottom. That's our water in tetrahedral geometry. So it's bent. Now, why is that important? It's important because, as we said, these have different electronegativities, don't they? So just like in HF, we would expect this bond and this bond to have a dipole. That means that this end of the molecule is going to be positive. On this end of the molecule, we're not only sucking the electrons away from the hydrogen, but we have two unshared pairs of electrons. So it's going to be very electron rich. We can confirm this by looking at the electrostatic potential lamp. We expect to see a positive end of our molecule shown by our dipole, and a negative end up here by the oxygen. The electrostatic potential map looks like this. This is water. We have a big red head up here on top, lots and lots of electron density, and down here by the hydrogens, we have blue. This is positive, and this is negative. Our conclusion here is that water itself is an extremely polar molecule. The fact that water is a polar molecule is actually the thing that makes water essential for life as we know it. All right. It also allows water to interact with ionic compounds and dissolve them. Dissolve them to form solutions, which we all remember are homogeneous mixtures. Now, the reason that it can dissolve it is the fact that this is very, very polar. Let's look at a little clip here. This is going to show a hypothetical crystal of sodium chloride. The sodiums are the little gray guys, the chlorines are the greens. Water is going to come in. It's going to remove the atoms from the surface of our crystal here and take them into solution. So let's watch that. Pay attention. There goes the sodium, by George. We got a chloride coming off, another chloride, another sodium, and this process will continue on and on and on until our crystal is dissolved. But I hope you were paying close attention, because this process is not random. The way that the water interacted with the ions here was very specific. If you were paying attention, you noted that every time we pulled a chloride off, the water was oriented so that the hydrogens were pointing towards the negative charge. Something like this. There's our negative charge. All of our positive ends are pointed inward. For our cation, just the opposite. The negative ends of the water molecules are pointing towards the positive charge. Now, the one thing that nature really, really doesn't like is an isolated charged particle. Doesn't like it at all. That's what lightning is. So, what we have done by placing water around these ions is to take this charge, spread it out, and stabilize it. That's the magic that water can do. Let's expand on that. This is the electrostatic potential map for the sodium cation. It's blue. What I have done is I have placed three waters around it with the oxygen ends, those are the negatives, pointing in. What I'm going to ask my computer to do is calculate an electrostatic potential map for this entire complex. When I do that, I get something that looks like this. Our big blue guy is in the middle here. Here's our waters. The blue is entirely gone. Even a little bit of yellow there now. The water has been able to take the positive charge and disperse it over the neighboring water molecules. This is what allows water to dissolve, break ionic bonds, and dissolve the sulfates. It's an amazing property. We will see in chapter 8 that water doesn't actually exist in groups of 3. It's more like 8 to 12. When you do this calculation over a larger group of water, the results are even more astounding. But that's chapter 8. Any questions? All right, let's just do a couple quick definitions here. If a substance dissolves, it is said to be soluble. All right? When we say solubility, we're talking about a number. That's the maximum amount that can be dissolved under a set of conditions. For example, 298 K is room temperature. We'll talk about that, chapter 9. Same thing with 1 atmosphere. But if we're at room temperature in the room, magnesium carbonate, you have a liter of water. You can dissolve 0.53 grams in that 1 liter. That is its solubility. All right. When we have a solution that has as much in it as it's supposed to get, so that's our 0.53 grams, we say the solution is saturated. No more will go in under these conditions. But you can actually cheat, okay? Turns out that things are more soluble, typically, if you heat up the solution. So, if we take our solvent, the thing that does our dissolving, put our solute in there and we put in too much, we can warm it up. More will dissolve than it's supposed to. Then, if we let it cool down very, very slowly, we can get a solution that's called supersaturated. Think about fries. There's our standard fry. This is super fries. Same thing. We're going to get more of our solute into the solvent than is supposed to fit. It's kind of a neat experiment to do in lab. So this is a solution of sodium acetate. We have taken and put in way too much sodium acetate than would dissolve at room temperature. Heated it up, it all went in solution. Then very, very, very gently, we let this cool down, not so much as breathing by it. It's all in there still. It's a super saturated solution. What we're going to do is take this flask with this long neck. We are going to drop a single crystal of sodium acetate down here. It will hit the liquid. Kind of a neat thing. Let's watch. It's going to land about there. There it goes. Instantly, we get crystal growth. The entire flask, within a few seconds, sets totally solid. When we're done, the liquid that's left is saturated, and all this excess we had in here because it was a super saturated solution. This also gets really hot. Think about it. We had to put energy into the sodium acetate to get it into solution. So when it came out, all this heat is now released. Any questions? Really neat thing to do. Really difficult to do because the solutions are so fragile. You walked up and you tapped the thing, it would go. Walk too far through the room, it goes. Very, very fragile, but neat. All right, let's talk about solubility. What dissolves what? There's a very simple rule of thumb, and that is like dissolves like. When we're speaking of things that are like or not like, we're talking about polar or non-polar. Water, we know, is a polar solvent. If we take water and we add alcohol to it, okay? Alcohol has an OH group. CH bonds are very, very non-polar. But the OH is very polar, just like the OH in water. Because of that, this polar hydroxyl group will make alcohol totally soluble in water at all proportions, called miscible. So polar solvent, polar substrate, totally dissolves. However, if we take a non-polar solvent, this is actually olive oil. Olive oil is a is carbon-hydrogen bonds in long chains, very nonpolar, polar solvent, nonpolar solute. It does not dissolve. If we had a nonpolar solvent, it would dissolve. So quite simply, like dissolves like, where we're talking about the polarity of the solvent and the polarity of the solute. Now, once we get something in solution, another interesting property emerges, and that is the ability to conduct an electric current. If we take an ionic solid, dissolve it in water, that solution will conduct electricity. That's why you can't take a hairdryer in the bathtub, right? Or you could do it once, but that's it. All right, this solution is called an electrolyte. Basically, it conducts electricity. Now, there are things that dissolve that don't form ions and do not conduct electricity. They're called non-electrolytes. Classic lab experiment from when I was a child. What you do is you have a beaker with your stuff in it. You have two metal plates, hook it all together, and put a light bulb there. Now you make an electric current. Back in my days, they were not very concerned about general chemistry students, and so this sucker was plugged directly in the wall. You talk about something that was extremely dangerous. Wow. So, if we take our solution, this is a non-electrolyte, the bulb doesn't light. But if we change this to something that's ionic, we get a really nice bright burn on our bulb. This is called a strong electrolyte. This is a really killer solution. If you're setting this up and you just happen to stick your pinky in the water, you're toast. Okay. Very, very dangerous. Somewhere between non-electrolytes and strong electrolytes, there's a middle ground. They're called weak electrolytes. So your bulb burns just a little bit. For a weak electrolyte, we're talking about something that dissolves, but just forms a handful of ions. An example, this is acetic acid, the acidic component of vinegar. If you put this in water, water can break this OH bond, give hydronium and the anion. These are ions, but this is an equilibrium process. We'll talk about that in Chapter 8. And this equilibrium is such that basically 100,000 to 1 is our ratio. We have mostly undissociated acetic acid, and every now and then we'll have one that ionizes. So it's a weak electrolyte and a weak light bulb. Again, we'll talk more about this in Chapter 8. Today, we don't use things plugged into the wall because we respect your lives much more than they used to respect ours. Today, we use little meters run by a battery, digital output. You put this in a strong electrolyte solution, you get a number. The units are microsiemens per centimeter, and it just shows the number. This is for a strong electrolyte, nice big number. If we go to a weak electrolyte, we get a much smaller number. And if we do a non-electrolyte dissolved in water, we don't get 0. Again, chapter 8 will understand why, but we get a very small number. The bottom line on electrolytes and non-electrolytes: if you form ions, it's an electrolyte. If you get just a few ions, it's weak. And if something like glucose dissolves nicely, doesn't form ions, it's a non-electrolyte. Any questions? All right. Well then, let's move on to the concept of molarity. Molarity. In the last lab that we did, you did a lot of reactions in solution, precipitation reactions. Reactions can happen in solution. In order to be able to do that quantitatively, we need a concept like molarity that tells us the number of moles we have in that solution per the amount of solution we have. Molarity is going to be defined as the number of moles divided by the number of liters. Now, in order to measure your volume for something like this, you would use what's known as a volumetric flask. Volumetric flask has a little line etched right here. And when you fill this flask right up to that line, you are exactly at, in this case, 1 liter. You get these in all sorts of volumes. 1 liter like this. Now you've added your liquid here, right? You know what's in it. That means you know the number of moles you have here. In this case, we have 1 mole. 1 mole in 1 liter. Molarity of this is 1. Come on, that's cute. All right, the way we would do this in reality. Molarity is represented by an uppercase M. M stands for molarity. It's important that you remember that this is uppercase, because when you hit general chemistry, turns out that there's another concentration term called molality, and it is a lowercase m. It's one of the cruel tricks they play on you in general chemistry. But okay, so we're using molarity, uppercase M, to show the number of moles per liter. To do this experimentally, moles of solute, volume of our solution in liters. Here's our volumetric flask. What we're going to do is take our flask, we will take our solute, we will weigh it. Once we know the mass, we know exactly how many moles we have, right? So we know how many moles, and we will add that to our flask. Once we have this, and again we know the number of moles, we will simply add our water to this and bring it up to the 1 liter mark. We know the number of moles, we know the volume, calculate molarity. Simple concept, right? Yes, it is. Let's do a problem. Here we're going to take sodium bromide. We have 3.25 grams, is 102 grams per mole. And we have this in 1,250 milliliters of solution. What is the molarity? Well, in order to do this, we need to know the number of moles of sodium bromide. We need to divide that by the number of liters. Now this is milliliters, so we have to divide this by 1,000. We could do that. To get the number of moles, we have a mass, we have a molar mass. We can always remember, mass divided by our molar mass is going to give us moles. Once we know moles, just divide it by liters, and we get molarity. So, mass over molar mass is moles, 3.25 over 102. We're going to divide this by the number of liters. Take our milliliters, divide by 1,000, 1.25. As we look at this expression, grams will obviously cancel. We have per mole here, that's mole minus 1, and it's in the denominator. Well, mole to the minus 1 is 1 over mole, isn't it? And it's in our denominator. So what we have here is basically 1 over mole. Now 1 over something is called a reciprocal. Reciprocal means you turn something upside down. So here we're turning mole upside down twice. If you turn something upside down twice, you're back where you started, aren't you? So this is just mole. 1 over mole is mole. Mole comes up. Now we do our simple math. 3.25 divided by 102 divided by 1.25. We get 0.025 moles over liters. Now this is 0.253 molar solution. The uppercase M can be shown simply as an uppercase M. When word processors came out, people started using an italic just to make sure you knew. Or they underlined it. Or they used a fancy font and used a script M. But it's always uppercase. These are all suitable for molarity. And you'll see them all. Any questions? Simple calculation. Here we're taking 6.5 grams of sodium acetate. There's its molar mass. And we have 1450 mils of solution. Again, what's the molarity? Same procedure. We need to know the number of moles, and we're going to divide it by the number of liters. This again is milliliters. We'll divide this by 1,000. For moles, mass over molar mass is moles. All right, going to divide this by the number of liters. Grams will cancel, per mole will come up top. 6.47 divided by 82 divided by 1.45. 0.05 moles per liter, or 0.05 molar. Again, thanks to word processors, If you're writing this out on a problem or something, moles and then liter minus 1, same thing as this, is a little more, well, it's easier because you can fit it on a line, or simply use molar. Any questions? See, these aren't difficult, are they? Potassium hydrogen phosphate. We have 238 grams, dissolved in 275 mils. What's the molarity? Take those numbers, set it up. Mass over molar mass divided by volume in liters. And let's see what we get. I'll pause for a moment. Here's our molar mass, there's our mass. We have more than a mole. Again, we have milliliters, have to convert those to liters. Mass over molar mass, it gives us moles. 275 mils is 0.275 liters. Grams cancel, moles comes up top. .469 is your calculator answer, or 497 to 3 significant figures. Any questions? Well, good. There's a tutorial, or actually 3 tutorials for this chapter. This one is everybody's favorite because it's a table. That makes it really simple. You will be given molarity, moles, volume, something will be missing. And you just type in the missing value. All right, here we are missing molarity. We have moles and we have volume. We remember that molarity is simply moles divided by volume. That couldn't be simpler, could it? Moles divided by volume. Moles divided by volume must be in liters, remember that. 0.976, 2.15. We're at 0.454. Now randomly, as you hit a new problem, something else will be missing. Here we're missing the volume. You've got to remember something. Molarity is moles divided by volume. That means that volume is going to be moles divided by molarity. So we solve for volume. Volume is moles divided by molarity. Substitute. Do our simple calculation. And we're 4.26 liters. Let's do one more. Here, moles is missing. Here's our basic equation. What's moles going to be equal to? It's going to be our molarity multiplied by our volume. Okay. Moles, molarity multiplied by volume. Simply substitute. 0.365 moles. Now what we've done here is actually going to turn out to be something useful and worth remembering. To get moles, we took our concentration and multiplied it by the volume. So just like you remember mass over molar mass is moles, here's another one. Concentration times volume is moles. We'll use this a lot. It's worth remembering. Concentration times volume is moles. Any questions? Well, let's look at some problems. These are old exam problems. This one, I believe, was an extra credit on exam 2. Solution is labeled 0.18 molar potassium chloride. What volume do we need to have 100th of a mole of KCl? Well, we're looking for 100th of a mole of KCl, right? Molarity is moles divided by volume. To get volume, we simply need to take moles and divide it by concentration. So, take our equation, rearrange it, and solve it for volume. Our volume is going to be the number of moles divided by moles per liter. Moles will cancel. Per liter in the denominator will come up top. 0.01 divided by 0.18, we get 0.056 liters. Sometimes I would ask this in terms of milliliters. Again, just multiply it by 1,000. Extra credit question.
Just to reassure, so basically that's how it's going to be every single time. We're going to have to divide the mole by the liter.
Yep. Oh, this is a fun one. This one allows us to use Avogadro's principle of number of particles per mole. We want to know how many molecules of sucrose, this stuff, sugar, are there in 300 mils of 2 molar sucrose. Well, in order to do that, the first thing we have to do is to figure out the number of moles of sucrose. We know that 1 mole will contain Avogadro's number, that's 6 times 10 to the 23rd molecules. So, let's start by determining the number of moles of sucrose. What do we have here? We have a concentration and a volume, don't we? Molarity is moles divided by volume. Moles, concentration times volume. We take our concentration, multiply it by our volume in liters, must go to liters, to get the number of moles. Concentration, volume, multiply them together, we get moles. Now we know how many moles there are. We know that 1 mole is 6 times 10 to the 23rd molecules. So we'll take moles, multiply it by Avogadro's number, moles cancel, multiply these two guys out, 2 times 10 to the 23rd sucrose molecules. Any questions? Sometimes you'll see problems that require you to use a mole ratio. This is one of them. We have potassium sulfate. We have 150 mils of 2.5 moles. Already you know concentration times volume is going to give us moles, isn't it? Okay. The question is, how many moles of potassium ions are there, and how many moles of sulfate? In order to calculate moles, we do concentration times volume. Then we're going to look at potassium sulfate and ask what our mole ratio is. Potassium per potassium sulfate and sulfate per potassium sulfate. But first, it's important that you remember what happens to potassium sulfate when we dump it into water. And that's what this is supposed to show. It's a super silly movie, potassium sulfate in a beaker. As soon as it hits the water, it totally dissociates. You will get 2 ions of potassium and 1 ion of sulfate. Mole ratio, 2 potassiums, 1 sulfate per potassium sulfate. Totally dissociated. So, concentration times volume gives us moles. We multiply that out. Cancel our liter and per liter. We're dealing with 0.38 moles of potassium sulfate. All right, how many moles of sulfate are there? You do your mole ratio. There's 1 sulfate in every potassium sulfate. So we're going to multiply this ratio by our number of moles. And when we do that, moles of potassium sulfate cancel. We have 0.38 moles of sulfate. So the same number, 1 to 1. For potassium, moles of potassium, the mole ratio is different. 2 potassiums for every potassium sulfate. 0.38 times 2 divided by 1, 0.76. Any questions? Well, this brings us to the second tutorial for this chapter. Mole-mass relationships. What volume in mils? In this particular tutorial, you are typically going to have to do at least 1 metric conversion. So here we're going to do a volume. We're going to get the volume in liters because molarity is defined in liters. We have to convert the final answer to milliliters. All right. We have a 0.05 molar solution of methanol. Have its molar mass. We want 0.037 moles of our solute. That's the methanol. We're going to calculate our volume. Moles divided by molarity is going to give us volume. We've done this. Substitute. 0.037 moles, that's this guy, divided by our concentration, 0.05 moles per liter, gives us 6.666 liters. In order to answer the problem, however, we have to do liter to milliliter. There are 1,000 mils in a liter, so we multiply this by 1,000, and we're at 666. Another problem. Milligrams, okay? We're going to have to do from grams to milligrams. Again, that's a factor of 1,000. How many milligrams in 0.77 liters of 1.13 molar solution of methanol? Well, here we are given a concentration and a volume, aren't we? That gives us moles. If we know how many moles of methanol we have, and we know its molar mass, we can calculate the mass in grams, and then multiply by 1,000 to get milligrams. So let's do it. Concentration times volume is moles. Substitute, multiply, we're dealing with 0.87 moles. Secondly, we know the molar mass. Convert moles to grams using a molar mass. Number of moles, grams per mole, moles cancel. We're left with 27.9 grams. Finally, grams to milligrams, factor of 1,000, we have 27,900 milligrams. Any questions? Well, let's do one more. Here we have a solution of calcium nitrate. Is 1.75 molar. We want so many moles of our solute. So we're looking for volume again. Volume we know is going to be moles divided by molarity. Moles divided by molarity is our volume. Simply substitute. We wind up with 0.05 liters. Convert it to mils by multiplying by 1,000, 50 mils. Again, all of these problems are going to involve one simple metric conversion, both on the web here and on Blackboard. Pay close attention to that. Beginning to do the last step just is infuriating. I know. All right, more test questions. Here we have a solution with 10 grams of sodium hydroxide and 500 mils of solution. What is the molarity? We look at this and we say, okay, molarity is going to be moles of sodium hydroxide divided by our volume in liters. 500 mils, 0.5 liters. Moles of sodium hydroxide, we are given a mass and a molar mass. That can't be simpler. Our grams cancel. Moles goes up top. 10 divided by 40 divided by 0.5. We have half mole solution. Any questions? Another one. How many grams of calcium nitrate do we have to dissolve to make 500 mils of 1 mole? Well, number of moles is going to be concentration multiplied by volume, isn't it? So we substitute 0.5 times 1. 5 moles, I can do that in my head. So we need 0.51 in 500 mils. 0.51, and we're looking for grams, aren't we? Do our cancellation here, 0.5 times 164, oops, sorry, 82 grams. Basically, half a mole, half a liter. Another extra credit. We have a solution of 0.375, a total volume of this, how many moles? Well, that's a simple one, isn't it? Don't you wish that would be that way? Again, we're going to simply solve for moles. We have a concentration and a volume. Multiply those together. Moles, concentration times volume. We are looking at 0.178 moles. Typical extra credit question. One more here. We have sodium chloride in solution. We let it sit on the bench top until it evaporates. We very carefully scrape out the solid sodium chloride. We have 1.5 grams. What was the molarity of the original? What we have here is a mass and a molar mass, don't we? We also have a volume. Our molarity is going to be the number of moles divided by our volume, which was 0.2 liters. Our moles going to be our mass, 1.56. Our molar mass, 58. Grams cancel, moles goes up top. 156 divided by 58 divided by 0.2, 1.33. So molarity problems. Some of these can sound odd, but there are just a few things you need to remember. Molarity is moles divided by volume, and it's also useful to remember concentration times volume is moles. Any questions? All right, our last topic here is solutions. So we have a solution, we add water. We get a different concentration, don't we? All right. There are two types of dilutions that we typically do in chemistry. One is called a serial dilution. In a serial dilution, the advantage here is that you can wind up with a solution that is extremely dilute, but you know its concentration accurately. So if we wanted to make something that was like 10 to the minus 12th molar, weighing out that much solid would be really tough. But what we do here is a series of dilutions where every step we dilute this 100-fold. What we do is we start off with a given solution, a liter of it. we will take 10 mils out and add it to 990 mils of water. When we do that, we have diluted this 100-fold. We then take 10 mils of this guy, add it to 990 mils. We have now diluted this 10 to the 4th fold. We take 10 mils of this, add it to 990. We're at 10 to the 6th fold dilution. And we do it again, we will be 10 to the 8th fold dilution. This again allows you to take a solution and make something that is very, very dilute, but the concentration is accurately known. Serial dilution. This is also used in what are known as homeopathic drugs. Now, homeopathic drugs are things that are not regulated by the FDA because the concentrations of the active ingredients are so incredibly low that they don't do anything. So FDA says it doesn't matter. Those are just trace amounts. Okay. They do that using this same sort of serial dilution. Start off with something, wind up with something that is very, very, very dilute. Now, ever heard of strychnine? Strychnine is a poison. When I was a child, you could walk in Walgreens, and there was a bottle of strychnine on the shelf. You could buy it. Take it home. People used it to kill rodents. Little old ladies used it to kill husbands. Whatever. Strychnine. It's a poison. Now, things have changed, you would think. You can't really walk into Walgreens and buy a bottle of strychnine anymore, can you? But actually, you can. It's called cold calm. Children's cold calm. Okay. Turns out the active ingredients in children's cold calm includes strychnine. Let's look at the label. Start here with belladonna alkaloids. 6C, so that's 6 of our serial dilutions. Belladonna alkaloids. Lethal dose 0.2 milligrams, but less than 10 to the minus 14 milligrams in a dose. Good thing. This is called yellow jasmine. Again, it's a 6C. It's related to strychnine. It's a little bush. And if you like walking through the woods and you're wearing shorts and you walk through it, you can get enough on your legs that you fall over dead. Diluted 10 to the minus 12 of their starting sample. Lovingly called Nux vomica, that's strychnine. Less than 10 to the minus 8 milligrams per dose. So yes, you can buy strychnine. I don't think I would give it to my kid though, regardless how bad they were. All right, the other type of dilution, you have a solution of known concentration and you simply add water. Wind up with a new concentration. The thing that makes these problems simple and doable is that the number of moles of solute doesn't change, just the volume. You have a solution, you know how many moles are in it. You add water, still has the same number of moles, just a different volume, doesn't it? So your initial and your final concentrations, moles at least, are the same. If we say volume times concentration gives us the initial number of moles, volume times concentration gives us the final number of moles, and these two are equal. That means we can write V1C1 equals V2C2. Concentration times volume must be the same. That makes doing these problems trivial. Solution of sodium chloride, 0.53 mils. We take 500 mils of it. We dilute it to 1750. What's the final concentration? Okay. Moles does not change, only the volume. We will set up concentration times volume initial and final. We are looking for the final concentration. Final concentration is C2. Substitute everything. Here's C2. Solve for C2. 0.5 times 0.53 divided by 1.75. Liters cancel. We're left with moles. 0.15 moles per liter. Here we have a 2.1 molar solution of something. We want to make 1,600 mils of a 1.1 molar solution. How do we do that? Well, moles does not change. We know the initial concentration, 2.1 molar. The final concentration, 1.1 molar, and the final volume, 1,600 mils. All we have to do is solve for the initial volume. Concentration times volume, we're solving for V1. That's C2, V2, and that's C1. Moles cancel. 0.84 liters or 840 milliliters. The problems, dilution problems, are basically simple. Now our last tutorial in this chapter is dilutions. To what final volume? So we're looking for the final volume, that's V2. Should 140 mils of 2.3 molar be diluted if we want the final to be 0.56? V1C1, V2C2, we're looking for the final volume, that's V2. V2 is going to be C1 V1 over C2. Substitute. Here's our result in liters. Problem says, again, this happens a lot, final volume in milliliters. Simply multiply it by 1,000, 580 mils. One more. 440 mils, that's V1. 0.05 molar, that's C1. Final volume, 0.88, that's C2. What's the result? Oh, that's V2. What's the resulting molarity? That's C2. So we're solving for C2. C1 V1 over V2. Simply substitute. Do our simple math. 0.026 mole. Any questions? Well, that ends chapter 7. Chapter 8 is next, so next week here. Chapter 8 is acids and bases. We are going to do the concepts of pH. We're going to calculate pH and hydronium. Please bring a calculator. And before you do, make sure you know what buttons to get a log and what buttons or how to get to 10 to the x. Remember Wednesday we do the empirical formula. Please be very careful, read the procedure. This is our list of tutorials thus far. Now, I get questions constantly from people that kind of weren't really paying attention in the first half of the semester and are regretting it now. I have a policy that after we do chapter 9, we have what's called an amnesty weekend. So after we finish chapter 9 on Friday, Saturday, and Sunday, I will reopen tutorials 1 and quiz 1. If you are dying for points, this is your chance to make them up quickly and hopefully easily. It goes away on Sunday at midnight, never to reappear. Okay, that's after we do chapter 9. Again, this is our tutorial so far. Please do them. Thank you.